Hello there, welcome back to our channel. And on your screen, we have this differential amplifier circuit using MOSFETs. So we want to understand the performance of this circuit by analyzing it. So what we see here, we have the transistor Q1 and Q2. These are NMOS transistor. Why they are NMOS? Because of the direction of arrow indicates the direction of the current, which is from drain pin to the source pin, and the gate currents are 0 for both these MOSFETs. So let me write that right here. So these are your pins of the MOSFET. And we assume that Q1 or Q2 rather, or M1 or M2, whatever the convention you want to use. Let's say Q1 and Q2 are same. It means they have the same property. They are exactly matched. So they are identical transistors. Okay. And what you see here is you have a positive voltage source, which is 3.3 volt. You have a negative voltage source, which is minus 3.3 volts. So these voltage supplies are with respect to ground. And this is a perfectly symmetric circuit. On the gate pins of both the MOSFETs, you have a differential voltage, V1 equal to 1 volt and V2 is equal to 1 volt. So actually that's a common mode voltage because the difference between them is 0. Okay. We have seen that in our previous analysis. Now, when you have the MOSFET, based on its cross section, it has a width and it has a length. Okay, so remember the cross section of the MOSFET looks like this. You have a semiconductor, and this is the high N dope, heavily doped N plus regions, and then you have on top of it is oxide, and on top of that you have a polysilicon. So let's call it as a polysilicon. So this is your gate pin, and this is your drain pin, and this is your source pin, and then you have a channel here. When you apply a sufficiently positive voltages on the gate pin, the negative charge carriers from the P type of substrate. This is your P type of substrate where you have plenty of holes and minority carriers are electrons here. So this is P minus substrate or the body of a device. So from that, the electrons which are indicated by the red colors here, they are attracted beneath the interface of oxide and the semiconductor. So remember, this is your oxide or silicon dioxide. And then you say the channel is inverted. So N plus regions are full of electrons, N plus region at the drain side full of electrons. And when you have a sufficiently applied electric field across drain and source, all you have the current flow from drain to source. Actually, the electrons flow from source to drain, but conventionally we say that the channel is conductive, the circuit is complete, and you remove the gate voltage, and then channel is depleted, and then you don't have any current flow from drain to source. And that's how you use it as a switch, a very effective and very good switch. That's the so where is your W and L here? So W is actually a cross section from this point, from across like this, just like this. So that's your the cross section, that's the width of the device. And here the channel length is this one. Okay, so that's the oxide length, whatever you call it. So that's the channel length. So the channel length for each of these transistor are 0.3 micron 8 or 350 nanometer, and the width is 100 times larger, that is 35 micron for each transistors. Now, these transistors Q1 and Q2, they have a parameter called as threshold voltage. So that is the turn on voltage. So the gate voltage that you apply here must be sufficiently positive for the NMOS transistors I'm talking about, so that the channel is inverted. And to invert the channel fully, you need to have a sufficient positive voltage VGS, and then only your MOSFET enters into conduction. And that voltage is called as threshold voltage of the transistor, VTH. So in our case, we say that VTH and VTH2 are equal because we assume the transistors are identical, matched pair. And based on the fabrication and the parameter, your VTH voltages are set during fabrication, let's say about 1 volt or something like that. Now, this is a differential amplifier, so we want the transistors to be operated in the saturation region. It means the voltage across the drain and the source should be greater than or equal to the voltage across gate and source minus the threshold voltage of the transistors. Should be equal to, greater than or equal to. So this is also called as VDS should be greater than or equal to V over drive, where